Have you ever felt like programming was weak? Like working in a programming language was really a hassle and you had to do tons and tons of work to get the compiler just to understand the meaning of what you're working in? Have you ever felt like the kinds of mistakes you make are the kinds of mistakes that should be caught by the compiler and should never make it to production? Today I'm going to expose a radical and deep error in the history of computer science that has had repercussions for decades and has affected basically everyone who uses a computer. And I'm going to do it by showing you something. This is a collection of C macros which implements basically stuff from C++, right? What they've done is, because C does not have templates and whatnot, they've implemented data structures and stuff in C, right? And they've made it generic according to, type, right? And it's really, really complicated, right? If you look at this, it's really, really advanced, So this is an attempt to get something to into C that C does not really support, right? Using macros, right? And basically, you should think to yourself, why do C programmers have to do this, right? And the stupid answer, the answer that most people will probably give, is that just that C does not have classes and templates and whatnot, and so you're just not able to have this in C. Right? But the thing is, there are things that you will want to do in C++ that C++ can't do, right? There are syntaxes that you can't make. There's types you can't make, right? Like if you look at some Zig features, right? If you look up Zig, look at its, Zig has this cool feature where you can actually define integers of arbitrary size, right? Where's the here? Aha, here. Right? So you can define integers, right, of arbitrary size, right? And so this is a thing you can't do in C++. Not really, right? If you tried to create a U18 class in C++, it wouldn't actually work anywhere than an integer where it work. You couldn't use it to index an array, for instance. At least I don't think you could. I remember trying to do that, and I remember it wasn't possible, right? And so the thing is that you get the point. There's things that even Zig, right, can't do. And the core problem of computer programming languages, as they are typically implemented right now, is that they're basically just not extensible, right? The set of abstractions you have, the set of things that the compiler can do for you is limited. And it's so limited that they actually try to make it limited, right? Programming language designers actually try to make compilers have a definitely finite compilation time, which basically means it can't be Turing complete, right? Because you can't have an infinite loop. Otherwise, you could have an infinite compilation time, right? Hold on, this is the wrong thing. So anyway, I designed it. Hold on, that's not the right thing. I designed a programming language to solve this problem, right? Called Coder's Basilisk. And basically what it does is it avoids this mistake that compiler makers have made for basically ever, right? Instead of saying, well, my language has to be have finite compilation time and I have to have strictly defined syntax and all these other things, which basically mean that the compiler isn't programmable, I fully embrace the compiler being programmable. Anyway, so this is a tiny little hello world program, right? It just prints hello world. I can compile this and run this. Let me just go there. Program/hello world.cvas. right? And if I have generated auto out.c, hello, right? See, I've done this, right? I can even change this from right. So let's recompile it. Now, what this compiler does, right, is I've made it compile. C, and so this is that program, right? I make it compile to C, right? Because that's convenient. Right, and just push to the repository just in case. Anyway, so I've made this programming language, and you'll notice that there's this weird thing up here. And what this thing basically is this is metaprogramming, right? I'm actually defining a kind of macro type thing. This worksheet thing is it's a thing that designs macros. This is and what it's doing is it's taking this other weird thing, and it's putting arguments in here, and then it's passing whatever it receives here, right? So whatever text you put in these brackets here, all of this is being put right here. And this is not just macros, right? This is this is compile time. I have told the compiler how to write code for me, right? I'm able to fully program the compiler. Now, the way I do this is a little complicated. I have a reflection library, right, that allows me to have this codegen code, right? This codegen tag that says that something is compile time only. And then classes that are used at compile time only, I declare no export so they don't appear in the final binary. But basically, I have all this support code I've written to reflect properties of the compiler. And I've used that, for instance, here to make a recursive descent parser generator thing, right? So, I've written this thing that allows me to design parsers, right? And basically little programming languages, right? Then I use this to design pprint, which is that thing we saw in Hello World. Where's Hello World? So if we go to Hello World, this thing, pprint, is actually defined right here. And it uses CGRD parser. This is some CGRD parser generates pprint by basically writing this little mini language, right? And it has all sorts of different commands it can do. Right? It's a little basically toy example, right? It's not that useful on its own. It's just kind of an example of what metaprogramming can do, right? I've defined my own programming language, sort of here, right? It's like a domain specific language, right, for pretty printing, and it gives me this really nice syntax for printing stuff, right? So I can have more lines here, right? I can recompile this, right? Because I press print line here, it's going to print these each on separate lines, right? But also, if I want to, I can, like, for instance, write int, and then I can put an integer expression here, right? So I can have that. Right, and so this is a little example of using metaprogramming. What I've actually done is I've extended the syntax of my language to support this new little syntax here, right? What this effectively enables me to do is I am able to write extremely complex logic at compile time and have the compiler do incredibly complicated analysis for me. So if I go into I actually have my very own sort of reasoning system, right, that I've implemented, which is able to represent arbitrary concepts, right? And so what this does is it actually, has a sort of, and basically you can implement arbitrary compile time logic, right, just by implementing a set of rules that act on nodes using this, right? And this is supposed to be a sort of, it's not like AI, but it's like, it's artificial decision making, And so basically, unlike C, unlike C++, unlike Zig, I can actually take my compiler and I can add new features to it. And one of the things, this is another example, right? You saw here how C, if you wanted to add templates and stuff like that to C, you have to do all this sort of shitty stuff in order to, like, and they basically ghetto stuff, right? And C++, if you wanted to have, they had to bake templates into the compiler, right? Well, in my language, I actually implemented templated code as an extension of the language. Templating does not exist in the base level language of Coder's Basilisk. What exists is basically, it's just a C clone, right? It's like C, but it has a little bit of object orientedness to it, just to make it tolerable, right? But I actually wrote an entire templating engine, right? And it handles types and stuff, and there's all sorts of cool stuff, right? And I wrote all this code so that you could write templates, right? And then I wrote my own STL, right? So I have a vector implementation. I actually had to write it 3 times because I needed to write it for primitives and structs, and for classes. Classes have a constructor and destructor defined, right? So they have detour and somewhere I call ctor. Grow should call ctor. Yeah, I call ctor here, right? So I added templates to my language through the compile time extension system, right? And so you need to think about what would have happened if this was available to programmers in the 1980s, right? Like it should have been. Well, then compiler technology would have advanced really quickly, right? People would have been writing really, really advanced compile time evaluation systems for languages at the time. Like if C had this, then we would make Lisp look like primitive trash, right? So, and I could explain what all of this does and how all of this works, but it's not very important. All you really need to know is that programming languages are missing this feature of being able to being able to extend the compiler at compile time. Now, you might wonder how this is possible, right? Well, C++ has compile time code, but I can't add new features to the language. Yeah, that's because it does it wrong. If you go here, if I go to parser.c, this is my compiler. Hold on, where is it? Do meta. Okay. Repeatedly try meta program. This is for, and then this is calls this, right? So anytime that my language sees the @ sign, what it does is it looks for a function with that name that begins with parsehook _, right? So if I go to right, if I this function right here, if I wanted to call it anywhere in my code, I could just do @global, right? And so and then this would be called, right? And that's just an example, right, of how it works, right? And so what this enables me to do is I'm actually able to call code during parsing, right? In my parser, anytime that it sees an @ sign, it calls calls compile time code, right? And I use this initially here, right? I wrote the builder. This is the very first metaprogramming abstraction I wrote. And what this does is this just formalizes a particular input-output method that I do, wherein I take in @name, and then I have an argument, right? 1 or 2 or 3, And this is what Builder allows me to do. Builder allows me to create little syntaxes that look like this. And so that's what the Builder does, right? This is the very first metaprogramming abstraction I really wrote. And as you can see here, what I'm doing, I guess it's not entirely obvious, what I'm doing, but what I'm actually doing is I'm manipulating the list of tokens, right? I have a linked list of tokens that I modify, right? The source code of the program gets tokenized, and then it gets turned into, and then it gets fed to the parser, and then the parser, as it walks along, finds an @ sign, and then the compile time code has access to the. Where do I get that? Right? Where do I get the list of? Here is where I get the. This is where I consume a token. This is one of the actions that I'm trying to look for, where I actually receive. Here, CG peak. This is where I'm accessing the list of tokens, right? This here is accessing the live list of tokens immediately from the read head in the. Right, so I have the this function right here, right? It's calling this function, and it's seeing, it's returning the next token, the pointer to the next token, right? And so that's what this is doing. And basically, what this allows you to do is you can literally access the source code of the program, the whole compilation unit, from compile time code. And this is all compile time code, right? And as you can see, after I define builder and builder n is the version that creates. So builder n does @name that, right? Builder n does @name, and then it could be 0 or it could be 1, 2, 3. And that's what this does, right? And this is all compile time code. This is cogent, right? So this system right here is what compilers are missing. And you might still be wondering what this actually allows you to do, right? Well, what is the actual value compared to C++ or Rust or etc.? The ultimate value of all of this, right, is that because the compiler is extensible at compile time, right? Because I can ship new compiler features as header files, right? So I can just right? All I have to do to add a new feature to my compiler, I don't have to edit the source code at all. I don't have to edit my compiler at all, right? This binary stays exactly the same. I just have to write new files, in here, right? In standard meta to add new compiler features, right? And this is very powerful. And the reason it's powerful is that I can basically experiment and incrementally add new features to my compiler, or anyone can add new features to this compiler, and it can be public domain, it can be part of your project, etc., etc. It could be proprietary, doesn't matter, right? Anyone can access the compiler and modify it, and it works with the same compiler everybody has, right? You don't have to compile a new compiler or anything. If everyone has this compiler, which, by the way, let me show you guys how easy it is to compile my compiler, right? So if I just cc-03 star.c, right? This will give me a working compiler. Yep, this is a working compiler. We can actually compile programs for this using this program / let's build this, right? So we've compiled that. This is actually going to overwrite a.out. So, we've overwritten the compiler with this, right? Whatever, right? Anyway, so we basically, anyone can build this compiler, right? It's super easy to compile. It uses basically standard C99 as long as you have a 64-bit standard computer. It doesn't have to be x86. It can be ARM. It might even work on really obscure architectures. It might work on RISC-V. I haven't tested RISC-V. It should work. I don't do anything platform specific that should make it not work on RISC-V. It just has to, I just need 64-bit, and I need 64-bit integers, 64-bit floats, and I need byte addressable memory. Right? That's basically all I need. Right? And pointers need to be 64-bit. That's the other thing. Right? And then CBAS will work. So basically, I have this tiny, super portable compiler that, as you have seen, compiles to C, right? I could show you the code that this is code that my compiler wrote, right? So this is an example of a. This is, by the way, up here. This is all boilerplate library code. This is the C standard library, basically ported to CBAS. But if I go down a ways, eventually I get to, this is pre-declaration of functions, global variables. There's no global variables in this. Type decals, right? Apparently I didn't have errno in this. Oh, you know what it is? I implemented errno as a macro, right? If I go, right? So see, I have errno defined here. So this is how CBAS accesses errno. Yeah, but for instance, if all of the functions in the C standard, in the Coder's Basilisk standard library, by the way, there's a string library in here, but implements both C strings and Pascal strings. This is all this code, right? But this is C code generated from Coder's Basilisk into C, right? So I have this tiny little super extensible compiler that compiles to C, and it works with C code, right? So if I go to make clean, just because I don't want to push crap to the repository, right? When I go to 2C, this is all stuff that I use for compiling to C, right? So for instance, if I've actually fully ported GL 1.1, OpenGL 1.1, and OpenAL 1.1, right? I haven't tested OpenAL 1.1 that much, but I've ported every single function. I have tested OpenGL, right? I have ported every single function, right? I might have missed one or two but I really tried to get them all. I ported the entirety of OpenGL 1.1 into Coder's Basilisk so it can be used, right? So Coder's Basilisk can use C libraries, right? It's pretty trivial to port them, right? You see what you do here, right? You just make the Coder's Basilisk prototype, and then you do inline C, and then you call the C function, right? And this is pretty easy, right? And so what this enables an individual person to do is you can download the Coder's Basilisk compiler, build it for your machine, and immediately begin building programs. And these programs can work with C libraries, right? But you also get this thing of you can add new features to the compiler, right? And you can do it incrementally in little pieces, right? You can make tiny little domain-specific languages. You can, make all sorts of you can make things that just are macros, right? And by the way, I want to show you guys that this programming language has actually been used to do something, right? I actually wrote my own operating system on my own little computer architecture, right? We're in the operating system right now, and I have an assembler, right? Examples. This is all stuff that I wrote in Coder's Basilisk, by the way. Right, the shell, the kernel, everything was written in Coder's Basilisk. I'll show you that in a bit. I just want to, right. So this is an example program. It just displays a little spinner, But this video is not about my operating system, right? By the way, the file utilities are also written in Coder's Basilisk. Anyway, so let's look at the source code. Let's first look at the kernel. I wrote the kernel in Coder's Basilisk. This is just macro stuff, right? This is including the assembler. My kernel is extensible, right? I can add new features to the kernel by writing assembly code and then the kernel can actually live build it into itself at runtime. But so this is the kernel, right? It has its own task system. It's multitasking. It has memory protection and whatnot. So I've written an operating system in this, right? And I've not only written an operating system, I wrote the assembler. This is the code for the actual assembler, right? This is where all the assembler logic is in this header file. And we're still in boilerplate code. Okay, here's a little bit of stuff. This is where it pre-decodes identifiers into instruction names, right? And this is the lexer. This is a debug function I wrote for the assembler. Anyway, it's not important, right? I also wrote the file utilities for the operating system in Coder's Basilisk, right? So what I'm trying to tell you here, guys, is that this language is tested, right? I have actually done quite a bit of work with this language. I've done an enormous amount of programming with this language. It's actually so mature, right, that if I go in here, hold on. Actually, let me show you guys something else I made. It's so mature, guys. Right, so that I've actually made a game. I made a video game. I just made Snake, right? I made Snake in OpenGL. Let me turn down the volume here. I'm running this through Windows subsystem for Linux. So the audio is going to have some delay on it, but I believe this actually compiles for Windows natively too. So this is a game I made. Yeah, I know, not much of a game. And it plays music. Yeah, I know there's delay on the audio. Whatever. I'm bad at Snake. It doesn't matter how good at Snake I am, guys. And so, I have some let's compile one of my test programs. I think I finished this one. Let's try this. Does this work? Okay, this is apparently some weird texture test I made. I actually don't know what this is doing. Hold on, what is this doing? Hello texture. What is this doing? So what did it do? Updates texture. This is what pushes the string. This is anyway. So this is a little test program I wrote, and this is using a library I made for making graphical and audio programs, right? Called FunBass, right? FunBass is all about fun, right? It's got OpenGL 1.1 and SDL2 hooked up, and it can play noises and stuff, and can play music, And hold on, but where am I? Oh, I see. This is where I'm generating the. So what I'm doing here is I'm generating a black and white image, and what I'm doing is for I think every new row I'm rendering this, right? So this is counting rows and this is counting columns, and then at a particular position I'm writing in here a value, right? And this basically what this does is it creates that scrolling effect. So this is an example of live updating a texture to the GPU. So basically what I wanted to show you guys was that this project is fairly this language is fairly mature. It has lots of stuff in it. Unfortunately, it's not self-hosted yet, but I mean, I don't really think that matters very much. I think what actually matters is just that you can compile it from C and you can get it anywhere. And later on, when people are really using the language, if people really get together with this language, I can make it self-hosting if it needs to be. I don't think it needs to be, at least not right now. Anyway, so that's the missing link of software development. Hold on. That's the missing link of software development. The missing link of software development is making your compiler programmable, making it so you can add new language features, new internal compiler logic at every step of the way, right? You need to be able to not only write new stuff in the parser, you need to be able to write new semantic analysis, and you also need to be able to write code generators. Well, I forgot to talk about that, so I'll talk about that really quick. I was about to end the video there. Let me show you guys the 2C generator. This compiles Coder's Basilisk to C. So I can just, page down here, right? So what it does is it just traverses the AST. This looks at an expression node, right? This is a node inside of an expression, and it generates C code to do what the Coder's Basilisk code says, right? If I page down, right? This whole thing is less than 3,000 lines. Converting my language to C takes less than 3,000 lines. I also have a code generator for my little virtual machine here, right? Remember the operating system I ran earlier in the video? I used this code generator to create the operating system. This is all compile time code, right? So the way it works, right? In Coder's Basilisk, if I go to and I look at the kernel, if I go all the way to the bottom, there's this function called cogen_main, right? You might have seen this in the Hello World program. And basically what this does is this function here is responsible for compiling the compilation unit. When the entire unit is parsed, okay, hold on. When the whole unit is parsed, right? Hold on, compile unit, right? If I go to, I think it's actually in parser.c here. Where is it? Where is it? Compile_unit. Here, right, this function, right? If I go to compile unit and go all the way down to the bottom, the way it works is that after the entire parsing is done, right, and that includes compile time, code execution, and evaluating all the @sign stuff, it will then search the symbol table for cogen_main, which is this function. And when it finds it, it runs it inside of the compile time code executor. It's not actually important how this works. It just matters that this is how it works. That it runs the cogen_main function, and it prints out an error if no cogen_main function is found. And that's it, right? And so basically this right here, cogen_main called emit tpcpu, which is at the very bottom of this file. I believe we're in it right now. Yeah, right here, right? And it asks for a prologue and an epilogue, and basically the prologue is the stuff that gets emitted before the actual code, right here, and then the epilogue is emitted right here, right? But that's not important, right? Basically, what you need to know is that I've written a code generator which generates my assembly code. Let me show you guys what that looks like. Actually, let's look at the kernel. This is assembly code generated. Hold on, what's this? What's this huge array? Oh, this is, okay, I see. This is a huge block of memory I reserved in the side of the kernel. Okay, right. This is another block of memory. Right, so basically, this is code generated by my compiler by this backend, right? And so this is very, very powerful. What this enables you to do, by the way, what writing your own backends enables you to do, like this, is unlike something like Clang, where you have to rebuild the entire compiler in order to support a new backend. Is you can support a new backend just by having a new header file. And this is powerful for multiple reasons. One, it means that the compiler is extensible without actually rebuilding the compiler from scratch. Two, it means that I can cross-compile to the wind, right? So this is an example of cross-compilation, obviously. This tool does not run inside of my virtual machine. It inside of TBCPU, which is the name of this. It's the name of the virtual machine that my operating system runs on. I'm able to cross-compile. Basically, any Coder's Basilisk compilation is basically, it doesn't know if it's native or cross-compiling. It just does the compilation, right? And this is very, very, very powerful when talking about trying to set up a tool chain. If you are a programmer who's done cross-compilation of C or C++ or Rust, you know exactly what I'm talking about. You know how much of a pain it is to get GCC or Clang or Rust set up so it can compile for, say, the 6502 or for the Motorola 68000. It's a real hassle. But with Coder's Basilisk, all you need is a header file that you include in your code that makes it into M68K or 6502. And I know I'm not speaking with very nice English here. It's late at night. You might be able to see it's 6:35 a.m. on my desktop. Right? So that's that, right? And so that's the missing link of software development, the ability to program your compiler. In order for computer software to advance to the next level, we need to adopt programmable compilers, right? The compiler must be programmable. And I have implemented a solution, right? Now, if you want to get this language, right, if you want to get it, you can get it from this website right here, codeberg.org/get/codersbasilisk. Hopefully this is still up by the time that you're watching this video. You might be able to find forks of this on the internet somewhere. It's fully public domain, if you go to the license here, CC0 1.0 universal, yes. Everything in this repository, save perhaps maybe some binaries I compiled because, they would have bits of GCC in them, right? But basically all the code in here is CC0, right? Completely free of limitations, right? You can even look at my planning documents. I released them into the public domain, right? I even have I have dozens and dozens of planning documents, that are just like weird shit I've done over time. So this is all stuff that you can look at if you're curious about the history of the project. You can also look at the README here. So this is a public domain, easy to build compiler that works with C, can cross-compile to anything that you want. Just write a new backend, and you can add new features to the language. Super, super cool, super, super neat, super, super small, right? If I look at the size of the compiler itself, right, it's actually fairly small, as I recall. du-h. It's 372K. I believe that is not statically linked. So this is the size of the dynamically linked compiler. So this is a whole useful compiler, 372K, right? And then I suppose I should count the source code of the. 356K for the support library, right? For my standard meta, right? If I go look at my entire library, it's 1.3 megs. So that's that, right? You can get this right now. You can integrate this with your C programs. You can port new C libraries. I even, by the way, let me show you guys this. Because I know that anyone who's not still interested has already clicked off. Where is it? I make sock test 2. Alright, I actually have a networking library working inside of my language, right? Server. client, right? So what I'm doing here is the server opens a port, right? I can actually look at the I actually have my own networking protocol. I ported over POSIX sockets. I can show you guys that. This is an example of how you port a library into Coder's Basilisk, right? So this is I have this string here, right, that has stuff I want to shove into the binary, well, into the C code. Then I pass it in to emit C as the prefix. I have the standard library prefix, and I have internet sockets prefix. So I have this class px socket, and I just have some functions that operate on it. I also have some stuff that operate directly on the integer, the px socket integer. So px send and px receive, for instance, I implemented raw. So this is POSIX socket send and receive. Right. I just wrapped POSIX sockets, and I did it in a way which basically makes networking easy, right? So this is just a networking support library I wrote. It's less than 500 lines, guys. 414 lines, and there's several blank lines right here at the end. So this is this is using actually a messaging protocol. I actually designed a little messaging protocol, where I actually send and receive text. It's pretty cool, right? And I use message receive, right? And I have a buffer here which I can receive. There's also a malloc version of this where it receives, where you can have it receive the size of the message and then malloc it for you. But that's not safe networking code, right? So anyway, I just wanted to prove to you guys this is a mature project that has lots and lots of development to it, and it's fully public domain. You don't have to attribute me at all, even, right? And it has the missing link of software development. This is the first major programming language to fully adopt this paradigm of a programmable compiler, right? Not even Rust's procedural macros does what this does, right? And before you just throw away my work as being toy compiler crap, right, you should consider that I wrote an operating system in it. I wrote an assembler in it. The project has OpenGL and OpenAL in it. I wrote Snake in it. I've done all this work to tool it. It compiles to C, and it's fully public domain, right? It's not like proprietary or something. I'm not trying to sell you something. Hold on. So you should get this, right? And if you don't like my particular implementation, you can at least look at my ideas. You can look at how I implemented compile time code, how I implemented code generation. You can look at the structure of my compiler. It's all public domain. You can just steal it, right? And you can make a better one. If you feel like my implementation is a bad one, you can make a better one. And I hope you guys will think on this. Thanks for watching.